I've already done this. Yeah. Thanks. No problem.
Oh, never mind. But you still have
Yeah, it's still like yeah. Thanks.
the other kid. He was like oh, that was like the yeah. That's like pretty confusing. I think it was just overwhelmed. I was like, what is this? I wish that it didn't show the other slide. You probably need to adjust your resolution on this one. It's like clear the size. Yeah, again, exactly what I should do. No, I'm saying that your resolution, like system preferences, and then you want to see what's going on. It seemed like that was a lot smaller. Yeah, that's true.
Yeah.
Yeah, just jumps right into that. It might have reverted because you didn't press confirm. I think that that works, all right? That's it. Sorry that it's small. Okay, welcome everybody. I am not Burton, as you may notice. My name is David Healy. Burton is my boss. And I'm filling in for Burton, who I believe is out of town in Boston at a conference unexpectedly. So I am not Burton, and I am not as knowledgeable as Burton about these matters, but I do work with deep neural networks on a daily basis at Recursion Pharmaceuticals. So if you have a question and I can't answer it, I will just write it down and forward all of the unanswerable questions to Burton. Any questions before we get going? Is there like a little clicker here? What's this? There we go. Okay, so I take it that this is the third part of a 3-part series about convolutional neural networks. I'm just learning this now from the slide. No, I'm just kidding. I've seen the slides before right now. So you talked about. I think the framing of all of this has been in terms of ImageNet, right? Which has sort of been how innovations in convolutional neural networks have been published and have been proven and taken off. So today we're going to talk mostly about ResNets. ResNets are the greatest thing in the world and that have ever happened to convolutional neural networks or anything at all. And they are probably the deepest, sort of like deep learning has gotten deeper than it ever has been with the invention of ResNets. So raise your hands. Who has trained a ResNet before? Well, who has heard of ResNets before? Okay. Oh, good. All right. You might be not have to explain too much. All right, so this is, you've seen this graph before in previous lectures, yes? This is the history of the ImageNet ILS-VRC competition and the performance of the best models each year. So you've already talked about 2012, which was the invention of? Everybody remember the name of the net? AlexNet, right. And the first time that deep convolutional neural networks became a major player and a very drastic improvement. You've gone all the way through VGG. VGG is basically just deeper, thicker, bigger networks. You've talked about Inception and GoogleNet. Now we're going to talk about really, really deep networks. Really, really deep networks came about with the invention of ResNets, which stands for residual networks. So we're going to talk about what motivated residual networks and how they have improved the world of convolutional networks. I should say that like ResNets are like it right now with convolutional neural network. I mean, we'll talk about some improvements that have been made to them and some additional things, but basically ResNets are like the vanilla convolutional neural network now that you use, just because they are so good and relatively easy to train stable. Also Inception. Inception might be we'll talk about Inception. Okay, so just to put it in perspective, this is what the depth of the networks look like. If this is AlexNet with 8 tiny layers, VGG, which is huge and is still sort of like the biggest model that you can train that is typical for image classification, looked like this. This was the model in 2015 that won, right? This whole thing, 152 layers. This was enormous, you guys. 152 layers was crazy. 8 layers actually was crazy, like between 2 years before this. So for somebody to come out and say we have 152 layers of this neural network is just insane. Okay, this is a funny thing. I was winning ImageNet until a deeper model came along. This is how everybody felt when ResNet was presented. Okay, so this is ResNet. We're going to actually spend a lot more time doing this, but pointing out that the classification error was for the first time lower than humans. So this was sort of like a big milestone. VGG and AlexNet had been large milestones, but this was the first time that we were like, okay, these deep neural networks are now better than people at telling us what is in this image. So it swept every competition at ILS-VRC and COCO. Basically, I will talk a little more about this in detail, but what it was that it established this ResNet sort of block, which is 2 convolutional layers with a ReLU in between them. And then the like innovation part is this sort of skip connection where you take the actual input and you add it to the output of the convolutional layers. So what you're essentially doing by doing this is telling this convolution here to learn not a mapping f of x, but a residual. Okay, so here's what sort of motivated the study of ResNets. ResNets came out of, anybody know what institution? Microsoft. It came out of Microsoft. And everybody had sort of noticed that there was this trend with deep networks. So I want you to look at these. I'm going to give you like a minute just to sort of process these plots. And what it's showing you is on the left the training error and on the right the test error of a model that is training over time. And it's showing you, I don't know if you can see, but the light blue is a 20-layer network, like say VGG19, and the red line is a 56-layer network. So what I want you to do is look at this and identify the pair of lines that is surprising, or supposed to be. Like, what is surprising about this result? Maybe you already know the answer. Given that so many of you have heard of ResNets before, you probably do. But even so, just look at it and think, what 2 lines, like comparing which of these 2 lines is the surprising part, or the part that was sort of unexplainable at the time?
Sorry. False. The false. Okay, so the false are probably not surprising, although they do look interesting.
The falls are probably a result of the learning rate dropping. A very kind of a typical signature when you have a dropping learning rate. I'm going to give you like 30 more seconds, and then I'll call on somebody.
Is it because the deeper networks are performing worse?
Forming worse on.
So it's like 56 layer has a higher training error.
Yeah, training error. Okay, yeah. So this is the surprising part here. This is not necessarily surprising. Why not? Super common actually for you to like beef up your model and turn out that the test error is worse. Why? Overfitting, right? This is like the most common problem in all machine learning. You overfit your model. So the fact that the 56-layer model is not doing as well on the test error, and then the relationship between the training errors and the test errors are about what you would expect, right? If you're doing it right. But it's really this part, right? Why is it that a deeper model with presumably more capacity is doing worse on learning the training set? So this is a question that everybody had. They knew it wasn't because of overfitting, which is always the answer all the time. And so here was sort of like a framework for us, for framing this issue at the time. People said, okay, well, the problem is clearly not that the network is like incapable of learning that this cat is a cat. The problem is it just must be an optimization problem. It just must be harder to get there somehow if the model is deep. So here's, and this is just presented in words, but I feel like this is a very important point to think about in a sense. So let's say I have a 30-layer model. Here's 30 layers. Here's some input. Here's some output. Right? I'm trying to learn some mapping between the input and the output. We've got 30 layers, right? Now I'm going to move to like a 50-layer model. So here's a reason why you might think that this sort of like order training performance is a problem. Because if I were just to take this 30 layers and just put them here, let's imagine that even let's just say that this 30-layer model has found the absolute global minimum, right? Like it is as good as it can get. Let's even say that even with 50 layers, you couldn't get any better. At least you ought to be able to learn an identity with extra layers. Like, sure, I'll put 20 more layers on, right? Let's just have 20 layers at minimum should at least just be able to learn to do nothing and pass the same input on to the next layers and have at least the same performance. So this is sort of what people were thinking at the time. Like, what is wrong with neural networks such that this isn't true, it turns out. For some reason, if you add 20 more layers on, it's just like it can't even learn to do the same solution that it had with fewer layers and just learn a bunch of identities. So this is where the idea for rows was born. People said, why not make, like, let's make this suggestion. Let's say, model, we have all these layers, but you don't have to use them if you don't want to. So what we're actually going to do is have this sort of like, this thing here, where we're going to say, here's x, we're going to add an x at the end. So this f of x, which is what this is learning, plus x is going to be the output of this like little stack. And that way, this can just learn 0 if there's no use for these layers. So what we're going to do is essentially this. We're just going to say, let's just take whatever, every time we have some layers, we're just going to take the input, and we're going to like give it as an output, like the exact same input. And then we're going to say to the network, like, you can learn stuff, but you don't have to. And the idea is that it's actually really hard to learn an identity mapping with a bunch of stacked convolutions with like ReLUs or sigmoids or some, and batch norms. Anyway, in order to learn an identity, something that will just like, image and then a bunch of stacked convolutions and then an output where the output is just the exact same thing as the image, turns out to be pretty hard. That's an optimization problem. But what's easy, especially with ReLUs, is learning zero. Right? It's easy to just zero out all of the neurons. And so that's what we want. We give it an image, and then what we want is for the network to find it easy to just output a blank at the end. Zero out all the neurons. And then we'll just add the original input in, and now I'm done by the layers. So this is the key insight, like the key innovation that has allowed really, really, really deep networks, convolutional networks. So, are there questions? Yes.
So after this reversal, these new convolutional layers end up with just zero.
Yes, a lot of them do.
And does that affect the performance computationally of passing it through the GPUs? Because there's more hyperparameters.
More hyperparameters. So your question is something like, just because like there's more matrices being multiplied, and a lot of the matrices are not doing anything, does it affect computation? So the answer to that question is no. I think there are slides later in this deck about that. The answer is it's actually much easier. And the reason is that you can get the same kind of, you can have like, well, we'll show you. You can have like much smaller convolutions and much deeper of them, and the number of parameters of these things are actually quite low relative to say UGG, which is enormous. Yes?
So how does the network decide whether to use these extra layers or not? Does it look at the loss or?
Yeah. So that's an optimization issue, right? You could imagine, say, you're not going to start these off at zero. You're going to start them off, initialize them randomly like a normal neural network. So they're going to output something, and that output here will have, there will be a part of the loss that pertains to this arm and a part of the loss that pertains to that arm, and you're just going to gradient descent. We're going to, optimize to that. So the short answer is you let the network figure out whether they need or not. Okay, as an aside, what is Burton like as a professor? Is he like a pretty cool professor? Is he like hardcore? Is this a hard class or an easy class? He's pretty chill. He's pretty chill. Chiller than most. Chiller than me. Chiller than me. Cool. I was wondering. I kind of wanted to come sit in on this class, but see what Burton's like. It's not boss, but hey. He actually is a super chill boss. I like purposely switched to his team from the team that I was previously on. Mostly because it was more interesting work, but also because I like Burton. So he's a very chill boss. It's like my job is like super academic. Okay.
That's a good answer, especially because you're recorded. So.
Oh, am I recording? I'm sorry to ask. I was just curious. Nothing against my old boss, too. I really like my old boss. Let's go on the internet. Alright. Okay. No more personal stuff. Okay, so the actual way that you build resonance is that you stack these things. And that's what this is showing you here, is that these things, each one of these is one of these little double blocks with the skip connection over it. So, yes, typically 2 3x3 convolutions. Periodically, and I think probably you've seen this before, you double the number of filters and downsample spatially. It's like a very common thing to do, so that the filter maps get smaller and smaller and smaller, but you get more and more and more of them. Any questions about that? You talked about that before, right? Your question?
Well, I mean, maybe we're going to do this, but obviously with depth, like, the problem is the backward part, not the forward part. Is it just using the, intermediary, losses in order to deal with, a big machine?
Using the intermediary losses to deal with machine gradient. Okay, so that is a good question. Part of the Venetian gradient problem can be explained away by the fact that it can take a much shorter path backwards. So you could have these skip connections make it so that the gradient doesn't have to go through a lot of layers.
So this is solving that problem too.
This is partially solving the problem. We're going to get into some other architectures at the very end of this class that are more direct about that. But this is, one of the reasons that you can get deeper. Okay. Another thing is that there are no fully connected layers at the end, which is what you have with VGG and AlexNet. And really, the fully connected layers will kill you. Because the fully connected layers, I think I looked through the previous lectures, and I believe that you saw the numbers of parameters per layer, and the fully connected layers is just enormous number of parameters. The loss is getting split into a million different pieces and passed around. So instead, what you do is the filter maps get smaller and smaller and smaller and smaller as you go, and then at the end there's what's called the global average pooling layer. Talk about that. Okay, global average pooling. So you're familiar with the concept of a filter map, right? This is what the image is becoming. It's getting passed forward through the network. At the end, you just say, let's take the average. So you may start out with a 256 by 256. At the end, you may have a 16 or something image. It's just a very pixely filter map. And you just say, take the average of that entire thing. And that's a global average. So if you have, for instance, this one has 512. 512 of these at the end. That just gets crunched down. Now you just have 512 numbers. And what this does is it makes it so that the entire filter map. Well, okay. So the first time they did this, they had no. This was the output. They just soft next this. They soft next the global average. And what that meant was that each of these final things had to correspond to a class, which meant that I had to learn to make this filter map entirely just about one class, which was cool because then it was very easy to go back to the original image and see what part of the image, because you could see what part of this final filter map was activated. And since that was getting averaged, if this was the wolf or something neuron at the end class, you could see that if this was high, that meant that there had to be something activated in the wolf filter map. Am I making sense? Yes. Making sense? Okay, yes. So in this case, we are actually going to put a number of classes, sort of dense network. So it does do a combination of the final filter maps. That sort of answers. Did that answer your question? Okay. Did that answer your question? Okay. Right. So ResNet came out at a lot of different depths. 35, 50, 101, and 152. They'll all test on the image at 152. Obviously, the deeper you got, the better you got. Okay, so for deeper networks, they introduced what's called a bottleneck layer. And this is just so that you have fewer parameters. But what you're going to do is you're going to say, I have, say, 256 of this filter map. I'm going to squeeze it down to 64. It's still going to be 28 by 28, but now it's going to be 64 features, basically, 64 nodes. And then I'm going to operate the convolutions on those 64 nodes and then expand it back up to where I was before. And that just allows you to sort of save on some weights. So, we like to do this. Tinky, we talked about this before. Okay. Oh. Yeah, okay. Anyway, so you get to keep the filter maps the same size, but you can kind of scrunch them down. All right. So, in practice, let's talk about initialization. Here was a problem. The weight initializations, this is actually kind of an orthogonal problem. This isn't inherent necessarily to resonance. So you've seen something like this before, yeah? Yeah, okay. So the layer means are kind of like knocking around 0, which is what you want as the layers get deeper. When you use a normal weight initialization, so you talked about weight initializations. You talked about the Xavier initialization, right? Okay. So what people had been doing, which was based on some theory around linear models, was using the Xavier or I don't know how to pronounce that, initialization, where you take either a uniform or a Gaussian distribution around 0 with the variance 1 over the square root of n, where n is the number of layers or something. So number of nodes in the layer. So each layer's weights were initialized with like a small number pulled from a Gaussian or a uniform distribution. And what happened was when you use ReLU activations with that, this decays down. As you can see, the weights for the networks get smaller and smaller and smaller and smaller. And so they had to do a correction for that. And thus was born the Hay initialization, which basically draws from a distribution, scales up the distribution that was normally being calculated by a factor of 2. And that turns out to work. In case you're noticing up here, that should probably be a times NumPy square root. No, it should be family divided by 2. Don't worry about it too much. The main thing is that the Hay initialization is wider because you start out with a higher variance. And the upshot of it was that they could suddenly, this was actually kind of cool, they could suddenly get traction on some deeper networks that had not been able to even get off their ground because of this problem. Okay, so back to, again, the ResNets did fantastic. That's that slide. Better than human performance for the first time. And since then, basically, we've sort of stuck with this as the base for a lot of learning models. Okay, so complexity. We talked about this. So on the left is a graph of accuracy of various famous models, which were ResNet 50, 100, and 152 are these 3 issue ones right here. Inception, and then Inception version 4 was sort of like a ResNet plus Inception. So on the right you have a graph of the number of operations. VGG, outliers here. VGG 19 has an enormous number of parameters and a lot of matrix multiplication that has to happen just to embed something. And ResNet 50s are all the way down here. So they managed to decrease significantly the number of parameters while going deeper and deeper and deeper and allowing for the possibility of more hierarchical representations. So this was fantastic. Oh, the size of this, I think, is the memory. Yeah, the size on the right plot is memory. Yes?
So I guess I don't quite understand why fully connected layer has so many more parameters than a convolutional layer. Because you're still, I mean, you're still getting there's a lot of edges there in between those layers. Is it just?
Yeah, there is, but yeah. So convolutional layer, I guess the answer is that fully connected layers are fully connected. So if I have like, even 10 and then another one with 10, each of these nodes has to have a weight for each of the previous nodes, so that's like 100 weights, right? And then if I just have 10 convolutions, this, I may have like a 3 by 3, and that's just 9 weights. And then I'm going to use those same 9 weights across the entire image. Where in a fully connected layer, you're learning a different weight for every feature. And so in a convolution, so it's called weight sharing. And this is really actually one of the reasons why deep learning has been so effective in images, and not really, like you don't see in the wild deep, fully connected networks. Nobody uses them, they're not that good. Might as well use a decision tree or random forest or something, a lot easier. And there are people who work theoretically on trying to make deep networks, deep, fully connected networks be better. But this weight sharing, sort of like a regularization that prevents overfitting, and one of the reasons why images are one of the domains that has been affected by this. When does this class end?
6:30.
6:30. Okay. Do you take breaks or anything? Or I just like go straight through or through? I don't do it. Okay. I'm going to skip that. All right. We're going to now just talk about other architectures to know. Before we do that, are there any more questions about ResNets? Use them. Yeah.
So not specifically ResNets, I guess, but when you get such a large amount of parameters, do you have to do any sort of distributed training, or like does everything still fit on one?
Oh, that's a good question. So with a ResNet 50, most ResNet 50s will fit on a GPU. A GPU may have like 12 gigabytes of memory. That's pretty big. And so what you'll distribute the training, but you'll typically have a copy of the entire like weights on every GPU, or on a single GPU anyway, so they can be combined. I want to wonder if, so there are some movements to go less deep and more wide, and those are thought of as more parallelizable. I will say that I'm not like so familiar with parallelization of networks, but from my experience at Recursion, for instance, the models that we use and the data that we work on is very big, and we typically are able to fit ResNets into a single GPU. We may not be able to do many instances per batch, for instance, on a GPU, but typically you can fit at least one. I think there are bigger networks that do have to be parallelized. So,
My question is regarding max pooling.
Yeah.
So is it, so where do we know we have to use max pooling in the sense that can we do the same task without having a pooling layer?
Can you do the same task without a pool?
In the sense that, so max pooling layer does it reduces the size of the input. What if we have a convolution layer instead of that, and with the reduced size that max pooling actually gives us, and let the neural network learn the same thing, basically what max pooling does. In the sense that max pooling first of all loses information when we try to take maximum value out of it. So why not let the the neural network do the same thing for us. And if it does better than max pooling, then it's good for us as well.
Yeah. So that is a good question. I don't know how to answer that, so maybe I will not. So one thing I should note is that there are other ways to make the filter map smaller, like a stride. You can add a stride so that you're not applying the convolution at every pixel, and the output then will be much smaller. I think that here's just a generic. I'm not sure. Let me just qualify this that I'm not sure that this is the answer, but here's some intuition that I have. A lot of times, especially with ImageNet style kind of classification, what you want at the end is to have a filter map that with some sort of locality information on it. And global average pooling, first of all, doesn't take, sorry, not global average pooling, but max pooling, doesn't take any parameters. Right? So it doesn't add to the complexity of the model at all. And all it does is basically say, I'm going to have the model get less and less granular over this image over time. So if there's a gorilla in the image, I want the convolutions to be operating over a more pixelated version of the image, like a downsampled version of the image. In max pooling layers, I think, does it make it easier to do saliency mapping and figure out like what part of the image, for instance, triggered the, yes, this is a gorilla. Does anybody else have a better answer than that? That was not a great answer.
Are you talking about the translation variant feature of max pooling? Or are you just talking about that?
The what?
The translation variancy that max pooling provides. Were you talking about that just now?
So the translation variancy. So yeah, what max pooling is? You can just think of max pooling as downsampling. Right? You work with images. You're just like decreasing the what's the word I'm looking for? Resolution. You're decreasing the resolution of the image. And the more you decrease that, first of all, one thing that it enables you to do is, given a certain size of a network, you're able to learn more filters if you have smaller filter maps, right? And what you suggested earlier was maybe we should have it downsampled, but have it learn how to downsample, for instance. And that seems like a thing that probably people have tried, and it's probably a thing that I don't know too much about. But again, max pooling doesn't add any parameters. Whereas like having a convolution that downsamples would, or having stride even does. Yeah, and you still are able to get these sort of like, increase the number of features that you're learning about progressively, downsampled images. So like, at the end you could be like, oh, there's a gorilla and it's in the upper right corner because you've downsampled everything and now it's just like one pixel out of the 4. That was a terrible answer. Does anybody have a better answer? Somebody can offer it. Okay. All right. I'm going to go with, because it's no parameters. That sounded best. Okay. Any other questions? Any other hard questions? Yes.
Yeah, just to clarify on the ResNets, you do this global average pooling on the last convolutional layer for the set of filters. That's mapped directly to your labeling, right?
Well, yeah. So typically, no. I brought that up because that's how the very first people I think that did global average pooling did that. But typically, you'll have one more dense, one more soft maps,
Okay.
basically. Yeah. So you do learn combinations of the filter maps. But it's still, crucially, still somewhat easier than to, yeah.
So the follow-up then is, from what I've understood about, how to actually like use, like for example, take BGG, you cut off all the fully connected net layers, you add your own, and now you can train with like all the information BGG's learned, but on this new data set, for example.
Yes.
How do you do that with the ResNet? Like, do you just randomize the last fully connected layer, or do you randomize that last layer of filters?
Yeah, so you can like neglect to put the softmax on the last one, and then just add another dense layer if you want, and another softmax.
Okay.
I would say that that's a cool way to transfer. So, yeah. You can always also transfer from earlier layers. I mean, the later you go, the more it's going to mimic whatever ImageNet was trying to learn. For instance, if you're learning ImageNet, or if you were trying to transfer from an ImageNet model. Does that make sense?
Yeah.
So you can always just say like, oh, I'll just take like the 10th convolutional layer, cut it off there, add some more convolution after. Okay, so here are some. What we're gonna do is like hit like 8 different sort of other kinds of architectures that we haven't talked about yet in this class that you might want to know for historical reasons, or if you want to try it. So the first is network and network. The idea was, this is actually a pretty early idea. The idea was that here is a convolutional layer, and what we're doing is taking all those pixels, we're mapping them to, we're just doing like we're just doing a linear combination of the pixel values. And then we're applying some nonlinearity, but really we're still just doing a linear combination. We're weighting them and then adding them together and applying a nonlinearity. So somebody was like, well, this seems kind of actually unsophisticated. It seems like, why don't we learn, it's just like you were like, why don't we learn something instead of applying a max pool? Instead of applying a convolution, let's learn something more complicated to do with that little window of the image. And so they started putting little multi-layer perceptron, little fully connected layers that would, again, fully connect all of these pixels and run it through like a tiny neural network. And that would be the output that you get. So that turned out to be really influential of an idea. It's not a thing that, like a ton of people do. But in terms of things like inception modules and where people are starting to think about convolution, like, let's do one-by-one convolution. Let's do different sizes of filters at the same time and stuff like that. So this was an influential idea, precursor to GoogleNet and ResNet called networks. So that's called networking network. We also have identity mapping. So this came out like the next year after the people who did ResNets came out with this as well. And the upshot of this was, let's take all of the nonlinearities that we had. So before, remember, it was like X, you had X and then layer, and then you had the residual add. And then you had the ReLU after that. And they said, well, let's just put all that ReLU and everything inside of the convolutional arm of this, and more directly just pass the actual input from the previous layer to the output. And this makes it theoretically, I guess, easier for the network to just learn, to skip connections, basically. Because it's actually getting, not even passed through ReLU, it's actually, or batch norm array, it's actually getting the input from the previous. Okay, so this was just like, let's do ResNets, but a little bit different, and it turned out to be better. So why residual networks? Getting to somebody who talked about computationally efficient because it's parallelizable. So these people, they said, okay, ResNets are cool, and everybody was like, yeah, ResNets, look, we're doing like 1,000 layers instead of like 1,000 layer ResNets. And people were like, we're so deep, we're so deep. And these people were like, no, it's not the deepness. It's the fact that you were skipping, like, it's the skip connections. So they said what would actually be better would be to have a wider, or shallower resonate. Both because you can more easily parallelize a wide network than a deep network. And you can get F by K filters instead of F filters. So they just say, like, instead of 256, we're going to put 1500 filters. And the upshot was that they showed that you could get the same kind of performance out of a 50-layer wide resonant than you can out of a 150-layer normal resonant. What's weird is that later we're going to see an example of a kind of architecture where somebody took the opposite path and was like, no, it's not the skip connections, it's the depth. Does everybody want to sort of like take like a break right now? I feel like it's kind of warm in here, and does everybody want to like stand up and move around a bit? No? Just keep going? Want to get out of the class earlier? Okay. Here we go. So here's, res next. This is a big deal. This is the other thing that people use really commonly. Res next basically says, creators of res next. Res next basically says let's have a bunch of different kinds of paths. This should remind you of something. Inception. I think I heard something. It's kind of like inception-y in the sense that, like, let's have a bunch of different paths that then get combined at the end. It said it right on the thing. Okay, yeah. Stochastic depth. Well, this is cool, right? Who was asking about vanishing gradients? Yes. So vanishing gradients. People are like, look, this is a 152-layer resonance. It's still a lot, even though it's skipping, sometimes. It's still a lot of layers to be backpropagated through. So let's do like dropout, like dropout does with the whiteness of a network. Instead of dropping out nodes. Now let's just drop out like whole blocks, and that will help with the training time, help with vanishing gradients. But at test time, just like the dropout, we're going to use all of it. So this is cool because it's kind of like forcing the network to learn different levels in the hierarchy. Right? It's forcing it so like it might learn something useful between like this output and that output. But when you drop that out, you're forcing it to sort of say like, well, just forget what you just that hierarchical representation you just learned and try to do the same thing from a more basic representation. So let's call it stochastic depth. I gotta mention 2016. So you guys have learned like all of these, right? Google Net, ResNet. The one that won, there was like, in 2016, everybody came out with all these like slight variations on ResNet. The one that won was kind of boring, in my opinion, which is Ensemble. So they were just like, hey, guess what? We can do even better than all of you if we just use all these different, you have an inception, 2 different kinds of inception, a bunch of different ResNets, and we're going to ensemble them together. So, good for you. Good for you. Okay, so 2017, adaptive feature map reweighting. Whew. Okay, adaptive feature map reweighting. Okay, so these are called squeeze and excitation networks. The idea of a squeeze and excitation network is that you could learn to weight the different, so a layer will have, so with relatively few parameters, you can just learn to reweight the filter maps differently, or to apply a separate weight to the filter map. So you may have, again, 256 filters. This is like have like an image returns 56 features on each pixel. And then you squeeze it, which means you global pool it, which we talked about. Let's point at the actual slide, because that's what it's there for. So you global pool it. So now you just have like one number per feature of the. And then you learn a weight matrix that basically just apply, learn a different weighting of those. And then you take, so this is going through a normal ResNet. You take this and you say, whatever comes out of this, I'm just going to re-weight those filters by this number. So I'm going to re-weight the first filter that comes through here by whatever the brown number is that I learned. And it turns out that that does not take very many extra weights, and you can get some extra power out of that. So, yeah, to 2017, which, now that I know I'm on record, I'm super wary of saying stuff. 2017, I believe, was the last year of the proper ImageNet. They were like, after 3 years, we've done better than people. It's getting boring. Let's do something else like three-dimensional classification with like word data. So anyway, squeeze and excitation networks. Fractal net. Whew, okay. So fractal net. Yeah, these are the other people. These are the people other than the wide people who were like, no. It wasn't that. It was really the deepness. They were like, the deepness is really the key here. And not necessarily the residual part. So they said, here's what we're going to do. This is going to be called a fractal net. And we're just going to have like a huge distribution of numbers of connections between the input and the output. So yeah, the output can learn directly from the input. It can learn from something that's gone through one convolution, through 2, 3, 4. And this is sort of like what ResNets were doing, in that they could learn to skip the connections where needed. But this is sort of making them more explicit and not using the residuals. Oh, and you can also drop out, just like with the ResNets. You could drop out paths for training time, force it to learn on a lot of different scales. Okay, dense nets, big deal right now. Dense nets, in the dense net, every layer is connected to every other layer. Feed forward, not backwards. That's this is again, so you can see this sort of like, with all of these things, there's still sort of this pattern which really came about with resonance for the first time, which is, let's let the model decide which layer of filters, like which level of representation it needs. So instead of forcing everything to go through these convolutions and out the other side, let's let the model choose. Maybe it can classify an elephant based on a single layer of convolutions, and if it can do that, let's let it do that. So all of these sort of variations, but this concept was really important. It really started with resonance. But all these sort of variations have the same similar thing. Dense nets are just like, well, let's just connect every layer to every other layer, and then they have an explicit weight that they can learn. And that would be a lot less. Squeeze net. I actually don't know what squeeze net is. So, the upshot of SqueezeNet is that it's tiny. I wish I could tell you more. Okay, this is the next sort of thing. Meta learning. Meta learning is learning to learn. This is like, Google has been in the news a lot lately for this. Networks, like using deep learning to do deep learning. Using a neural network to tell you what neural network to make. So basically what you have is, this is neural architecture search. So people will use reinforcement learning. Do you guys cover reinforcement learning yet? No. Will you? Probably. Probably cover it. So anyway, you'll do reinforcement. And on the hyperparameters of a network, basically. And allow a different controller network to decide how many layers you're going to put, what the layers are going to consist of, how many nodes to put in each layer, which layers to connect with which other layers. And so out the back you get these crazy, like, they're not like, they don't look nice. They're just like all over the place connections and different sizes of layers and like visually unappealing, but they're very high performing. And you have basically a neural network controller, neural network that is learning how to put together neural networks that are better.
Is that people want to take the train?
Yes. Yeah, I think so, because you have to build a new neural network and then train it. But it's a little like hyperparameter optimizations. Yeah. So I think you'll probably talk about policy gradients more later. But yeah, we'll treat this as a policy and then keep the gradient back to policy. Oh, this is another big thing, which is this gets to your question. Yeah. Segue. Nice. So the neural architecture search is very expensive on ImageNet. ImageNet has like 2 billion images or something. It takes a long time to train, and a long time to even tell if the network is even good or not. So a lot of what people are doing is you're using this reinforcement learning to find a good cell structure. So first you'll have like these different blocks of cells that you can stack. So these are like, instead of let it come up with the whole network, we'll let it come up with a module, like an inception or resonant module. And then we can just stack these depending on, like if it's a hard problem, we can have deeper ones. If it's an easy problem, we can have shallow ones. And we'll optimize the module on a very small data set, and then use that. So that's more on meta learning. Meta learning is a huge deal. Okay, we're at the end. Okay, so in summary, before you talked about AlexNet, BGG, GoogleNet, and ResNet. These are the 4 big ones. This is a good class burden. And we also talked about these like 9 other sort of things. I don't think, for the purposes of this class, that you have to like know these other 9 architectures like the back of your head. You just have to be familiar with the kinds of things that people thought about after resonance came out, ways to improve it, or ways to do the same thing with a different architecture. Okay, so yes, these are all in wide use and available in model zoos. You all got a deep learning project, right? That's exciting. You can all use these models if you're needing a convolutional neural network. I would agree with Burton that the ResNet is currently the best default. Also, these squeeze and excitation networks. This is definitely true. There's a trend towards deep neural networks, even though we talked about some network architectures that have sort of tried to accomplish the same thing with fewer layers. I would say broadly the trend right now in the world is bigger, deeper networks. So skip layers, skip connections, and gradient flow to try to reduce them to gradient problems are sort of like the big goal. And the middle one. I think that's the end. Okay, are there any questions? Yes?
It's an idea with introduction value. How meta could you get?
Yeah,
Could you have
right?
something else creating a learner, and something else that goes in the circle?
question. I feel like I should have ready a cool example of somebody who like used did like 5 layers of meta, a controller for the controller and a controller for that controller. Yeah, I don't know. When's it gonna stop? It's a Russian doll situation.
Learning materials.
Yeah, that's true. We'll have another controller to figure out when to stop adding more controllers. Yeah. Any other questions? Otherwise, I think we are done. Good luck. Sorry?
Excited.